All right, so we're gonna get started again. Hope you got enough coffee, enough whatever you needed. I needed that for sure. So at this point, right, I just want to give you a quick recap. And for those of you new in the room, the recap may or may not help, right? Because it'll seem like something that hit you from the sky, right? So we said, why is hierarchical classification important? What are the challenges? And we talked about essentially three methods, right? I would say one is ignore the hierarchy altogether, right? The second one was take into account the hierarchy and ensure that the weight vectors that you're learning for your parent and the children are similar to each other. And the third one, which is higher cost, was a cost-sensitive version of the same thing, right? So that instead of enforcing this in the regularization, let's try to do this in the loss function, and now we can introduce any sort of hierarchical costs here, and we talked about that. Okay, so there are some strengths. The strengths are that these hierarchically inspired methods, right, will help classes that I like to call are poor, who have less training examples. The method that higher cost we propose has a better training optimization function in terms of like you don't need a MapReduce formulation, or the dependencies are kind of taken care of, so you can do this in an independent manner. So there is all this some benefits here. Prediction time, as someone pointed out, we're still doing the same prediction so far. At the leaf nodes, we fire all the leaf nodes, and we say, hey, who do you belong to? And based on that, we make the final decision. Okay, so that's where we are at this point. Okay, and so my group, right? So we have been doing this since some time, right? So that's why I can give a tutorial and I can sound a little bit more knowledgeable. But we've been doing this for 5-6 years, and every time we come up with these ideas, we say, oh, this should beat the flat like by 10 or 15%, right? Why like only 2 or 3%, and why only on those rare classes? So that always kind of like bugs us from a research perspective. How do we improve this even beyond that? So this other thread is related to trying to improve upon that, right? And another thing that we want to do is we want to now make the prediction runtime be better. So we want to now veer towards the top-down type methods. We want to say that if I was to come up with a real-time online system, I cannot afford to fire 100,000 nodes. So ideally, I would prefer top-down methods, because then I need to fire nodes in the tree, right, in the path of the tree, which might be 6 or 7. And we want to solve some other interesting ideas, or as you do research, you say there are some other extensions. So this next series now, it talks about this inconsistent hierarchical problem, and then I'll talk about some of these more little bit advanced topics. And as I said, these are more threads, so looking for ideas. And this is not only my work. I think this is work that I feel is interesting in the space that could really advance some frontiers here. And thanks for coming back. All right, so we have a predefined hierarchy, and this hierarchy is right now we assume. So someone asked this question: what if I don't have a hierarchy? Right? And I said you could do clustering, but clustering is not a good. You could do unsupervised methods, or you could try some other manual construction or things like that. But essentially, up till now, we assume that the hierarchy is defined by the domain expert, and it reflects the human view of the domain. And essentially, what we see is that this may or may not be the most optimal for your machine learning automated classification, right? So there's some issues around that. So give you an example, the domain will define this predefined hierarchy. We'll train a best classifier to given an instance, find me the path in that tree. Okay? So another motivation was, as I said earlier, this works well. The flat, which ignores the hierarchy, works really well. And it works well for well-balanced data set with small number of categories. It does have an expensive train and prediction cost. The hierarchical classification works well for rare categories by leveraging the hierarchical structures. It's computationally efficient if you think about the top-down method now. And it's preferable for large-scale data sets. But some benchmarks, right, have good performance with flat method and its variant. And our goal is, can we improve this using the hierarchical information that we have? So our goal is to beat the flat method when it does not do well. So why doesn't it do well, and can we improve upon that? So we first ran this case study, and this is a standard news group data set. I'm sure if you do any sort of text mining, you have done that. So so this also reminds me that many of the results that I presented so far are for text, But these methods cross-apply. So they've been applied to images, they've been applied to protein sequences, protein structures, and even like some product features, right? So just features about some products. Now, when we use text, we normally use the TF-IDF representation. So I didn't say that, but you could also use any other favorite representation. These days, word2vec is very popular and will give you an additional 5% boost if you do that. So here is our standard newsgroup data set. This is how the hierarchy is defined in the newsgroup data set. These are some news articles about these different things. And what I've done is I've tried to like highlight in star and in red some of the things that look to be misclassified, right? Like if you look at this tree, you think that something is incorrect about this hierarchy. For example, electronics class is within science. Windows.x and graphics are within comp. There is society, religion, Christian, but there's also some miscellaneous religion, and one is in talk and one is not in talk. So there is some like, already you see there is some like inconsistencies in the way the definitions are being presented, or the way, you know, things are being like, some are going 2 levels, whereas some are going 1 level. So there's some like inconsistencies already. So ideally what we do is, so in this case study, what we did is we tried to reconfigure the hierarchy, and I'll tell you later how, in these two methods. And what we notice is that our performance, this is micro F1 and macro F1, jumped from 77 to 79 in this case, and from 79 to 81 in this case. Okay. Now we did this initially. So we did this with the methods that we came up with. But essentially, what I want to show is that different hierarchies now result in different classification performance, right? Which means that there is something to do with how do you define these hierarchies, and if they are poorly defined, then you will of course get a poor classification performance. So the goal is how do we improve upon that. So I just want to say that these are the 2 methods that we talked about: the HRLR, which uses the regularization in the parent-child, and the cost-sensitive learning, which uses this hierarchy-specific cost multiplied by the imbalance cost multiplied by the loss that you have for your classification. So what we notice is that these methods which use this hierarchical structure, their performance does deteriorate if the hierarchy used is not consistent. So now we say, how do we define consistency, or how do we define what does it mean to be not consistent? So these are just some, I want to say that these are some thoughts and ideas that hierarchy is normally designed for easy search and navigation without taking into consideration classification problems, right? So they're used for search and navigation for the different taxonomies that you have. Sometimes the hierarchy is created based on semantics, which may be independent of data, right? And our classification depends on data characteristics, which is such as term frequency when you use a TF-IDF representation for a text document. So our expectation is that if we can do a data-driven hierarchy, then hopefully that can be much more powerful. A priori, it's not clear to domain experts when to generate new nodes or to merge 2 nodes in the hierarchy, right? So imagine you're faced with 100,000 nodes, you're trying to do this manually. It's going to be really hard for you to define the structure of the hierarchy. Also, this is more from bioinformatics world where different biologists, based on their country affiliation, believe in different hierarchies for the same data set, right? So based on the experimental protocol, or based on what they do, even though they're doing the same like functional annotation, they will define the hierarchy in slightly different ways. So which means it's not clear whether they are complementary or whether they're really not consistent. So different experts here come up with different hierarchies, and this will lead to different classification results. So we talked about that with that case study, but we'll come back to that. And large number of classes with confusing labels poses a unique challenge for manual design of good hierarchy. Something that happens so often is that data has its life of its own, right? So as time goes on, things get recategorized, reclassified all the time. This was essentially some analysis of, for example, the word flood, and usually it's not part of this geography class, but during the news cycle, when there was really this flood happening in a location in India, Chennai, then this became its own own category, right? So everything associated with Chennai became flood rather than flood its own geography class. So these are very adaptive changes that can happen in the data that you see. So what we want is we want to go from the predefined hierarchy to something which is data driven. and this will hopefully improve our classification performance. So I'm going to assume that now the methods that we come up with will essentially improve the hierarchy, and we'll still use the state of the art that we came up with previously to improve our further performance. So one can, so here is a, so not only me, but lots of people have been working in this space too, right? So there is inconsistent hierarchy. And if you look at the taxonomy of the different methods that exist there, then there are approaches which are called flattening or rewiring. And as the word flattening suggests, is you have a hierarchy and you're essentially removing some of those nodes and you're flattening the hierarchical definitions. And at some level, you are pruning off some of the internal nodes to create a hierarchy much more succinct, if you want to call it that. And based on what you do, whether you flatten an entire level or you flatten some specific nodes, you'll get different versions of your trees that will start existing. The rewiring involves changing some of the links, right? So it involves this node had a parent, you change its parent, or you remove the node completely, or you remove a parent completely and you rewire all the children to other parents. So there are all these other variants. And based on, again, in this space, what you do is there are some which are a little bit more expensive, like this using elementary operations, and there are some which also involve automated hierarchy generation or clustering. Right? So you do an unsupervised approach. You take your classes, you take your data, and you just do a clustering, and you say, I don't care about that expert-defined hierarchy. Here's a completely new hierarchy that I came up with a clustering solution. So there are all these like branch of methods that folks have worked on. So flattening strategy, right? So what makes sense? What doesn't make sense? Again, whenever we look at these, our perspective, or at least our perspective, is that we want to run this at least for 1,000 classes. We are going to have large number of examples, and there will be large number of features. So we're also going to focus on the fact that if a method is good, but it cannot really scale, then it's really useless because it doesn't really help us in our use case scenarios. So for large scale data sets, top-down hierarchical models are preferred over flat models because of their computational benefits, which is training and prediction time, right? So what is a top-down method? So up till now, we talked about flat, HRLR, and higher costs. Top-down method is independent, let's say independent classification models trained per node. And during prediction time, you're just going top-down, right? So it's very efficient during prediction time because I didn't need to fire all the leaf nodes. The top-down models suffer due to error propagation, right? So if you make error at the top, then you are kind of in trouble land because you're going to make errors at the bottom too, right? So top-down methods usually have poor performance than flat methods for sure, but then all the other hierarchically inspired methods because they suffer from this error propagation issue. So our objective is that can we modify the predefined hierarchy by removing or flattening inconsistent nodes to improve classification performance of top-down models. And our hope is that this will reduce the top-down error propagation due to less number of decisions for classifying uncertain examples. So if you just flatten some things, then your flattening involves removing some of those top-level nodes or internal nodes. So you are not making a decision at that level. You're making a decision to go to the bottom level. So hopefully that will help you. So that's the balance that we want to achieve here. So here are some older ideas. So there's a level flattening techniques where a single or multiple levels of the hierarchy is flattened. And based on the levels flattened, I hope you guys can understand these acronyms: top level flattening, bottom level flattening, and multiple level flattening. So very simple ideas, right? So you have your hierarchy. I flatten this entire green top level, and essentially these blue guys, they just go join the root node. So now during prediction and during training time, I don't use this hierarchy. I use this one where my classification decision depends on this level and then on this level. Now, one could say, why don't you flatten everything? And that's essentially our flattening strategy, which is you remove all the nodes, right? Now, the drawback in all these things is that all the nodes in the levels are identified as consistent, which may or may not be true and results in poor classification performance at the end, right? So this is like a hacksaw approach. You say, well, I'm going to flatten this level 1. I'm going to flatten this level 5. So this is a very make some strong assumptions about the flattening that we do here. So rather than flattening entire levels, why don't we flatten only subsets of inconsistent nodes? Why don't we remove those nodes that we think are the most inconsistent here? So if this is my original hierarchy, and let's say I removed this blue node and this green node, and then all I'm doing is I'm going to take these children and rewire to the parent, take these two children and rewire to their parent, and then I'm going to use this final hierarchy. So the criteria, the criteria to how to do this, define what an inconsistent node means, can be done by using degree of error that you're making at these nodes, by using some sort of a margin, some sort of a, when you're doing these optimizations, some sort of where the margins are coming out, or some other learning-based strategies. And this comparatively has better performance than this hacksaw approach, which was the level-wise flattening. Right? So now we are saying that instead of doing this, you kind of be a little bit more selective, and when you're doing the selection, there are some ideas there. Be a little bit more smarter in how you do this selection. Okay.
That's like a cubist rule.
Say that again.
It's like Ross Quinn's cubist rule.
Right. Yeah, it is at some level. Right. So one of the approaches that kind of works well, it involves what is called this local approach for inconsistent node removal, or level-wise INR. And essentially what we do is we identify the inconsistent nodes based on the loss function that we are seeing on the cross-validation set, right? So based on the loss function, the values of the loss function that we are seeing on the cross-validation set. And the criteria for flattening nodes is based on some threshold, which is some threshold away from the mean, right? So we'll say that any nodes that have some greater than mu1 plus sigma 1 will be flattened away at this level. Any nodes that are greater than mu2 plus sigma 2 will be flattened at this level. And the way this process will work is, this is my original set. I will take some portion of my training set. I'll learn these classification models. I will look at their loss function values, and I will prune away anything that goes away based on these mean and standard deviation. And then I'll say this is my modified hierarchy and retrain a new model on the modified hierarchy. The evaluation is still done on the leaf nodes. Right? So this is really the key, right? Just to be consistent. Now we cannot really do a hierarchical metric type evaluation, because the hierarchy out here is easier than the hierarchy out here. There are fewer paths here, right? So the evaluation always has to be done at the leaf nodes, just to be consistent and fair in comparison. So these methods also tried the level-wise, and they also tried what is called the global-wise, which is instead of defining a mean and the standard deviation per level, why don't we just try the mean and the standard deviation for the entire tree, and then prune based on that. So in this case, all the levels have the same threshold for the node flattening. So in practice, the global method works better than the local one, and it shows much better results than the level-wise INR. But these are, again, all that's happening is based on some criteria. You're pruning of some nodes which you feel are hurting your classification performance, and based on that you move ahead. There's no rewiring here. There's no changes to the tree structure except removal.
I don't know it maybe, but like for decision tree, supervised.
Right. Well, so decision tree will be a model that is trained per node. Remember that.
No, I mean like the decision tree is that. Do they ever? Is there any like research done on like once you build a decision tree, can you apply these inconsistent node removals on that?
I think there's lots of pruning strategies there, and I'm sure.
Usually
it's just level wise. I personally don't know, but I'm sure, they have been around for long. There's a lot of work done on that. I'm sure there is something related to that. So to compare how these methods perform, what we're going to do is we're going to train one rest model is trained for each node except the root and the hierarchy. The predictions are made starting from the root node. So now we're going to start assessing top-down methods, because our goal is to improve prediction runtime. So we don't care about those hard costs and HRLR, because they have a more expensive prediction runtime. And we start from the root and recursively select the best child until a leaf node is reach. Methods we try is top-down logistic regression, which uses the predefined hierarchy. There's no modification done. Top TLF, BLF, and MLF involve flattening the entire top level, some multiple levels in between, or the bottom level. And MTA involves hierarchies modified using the margin value, which is computed at each node. So I'm just going to show you some performance results here. These triangles indicate whether they are statistically significant with the p-value of less than 0.01 and 0.05. These are my top-down hierarchical baselines, and these are the level-wise and the global INF methods, right? So the level-wise and the global. And these are, again, some of those similar data sets that we saw earlier, the clef, diatoms, and IPC, and the DMOZ data set. So here I'm reporting micro F1 and macro F1 along the rows. Right? And you'll see that consistently the global INF outperforms the other methods here. So I think it just had more like less sensitivity, right? So the level-wise became much more like local sense. So there's only like 5 points at the top levels to make a decision. So you just get a little bit more sense. Pruning was on a held out data. So there was now you are separating your data into essentially four parts if you want to think it that way. Your training part is split into its own real training, 10% held out, and then real training set, and then you really go and check on the test set. So we also compared against the flat methods, and what I wanted to do here was show you the difference in performance when the number of training examples per class is less versus high, right? So what we see is that we get a bigger performance improvement for the smaller folks here again versus the larger classes, right? So for the smaller classes, we get a bigger improvement versus the larger classes. Again, so that's been the theme, and that essentially happens because now we're using the hierarchy, right, at some level, but we are also using the fact that we have pruned away the inconsistency. So our top-down method is starting to perform better compared to the flat method. So we did some more prediction time analysis here. So this is the flat versus the top-down methods, right? So this is the prediction time in minutes. This is for DMOZ small versus the larger DMOZ sets, right? So there's more time here. So clearly there is a big time saving, and this is what we were gunning for when we were doing this thread of work. And in terms of training time, the global INF and just the global INF has a little bit larger, of course, because you're doing some retraining. You're training on the held out set. You're making your decision based on the held out set. You're pruning your class, and then you're retraining the entire tree based on that. So there's going to be some additional costs there. So training time is going to be more, but the prediction time is the benefit that you're looking for. So that was easy. Flattening, right? Just remove some of these nodes. So the flattening strategy, although useful, has a few limitations. It cannot deal with inconsistencies in different branches of the hierarchy, right? So let me show you another of those color slides, right? So there is this original hierarchy. There is this 3 classes at the first level A, B, and C, and we have currently classified A.1, A.2 within A, B.1, B.2 within B, C.1 within C, and C.2, C.3 within C. If you notice, I put C.1 as a square and a blue just to show that it shouldn't belong here, but it should belong in this case. Now, if you just did the flattening strategy, then the best you could do is this, right? So you would have A.1, A.2, and then you could have C.1, just roll up to the root with C.2 and C.3. But ideally, what you want is a rewiring where you want this C.1 to move under the class A, right? So the flattening strategies cannot really do this given the nature or given the way that they are operating, the assumptions that they're making. So the hope is that we want to come up with methods that rewire, and this can use to resolve inconsistencies that occur in different branches of the tree. So this was a 2006 paper, so exactly 11 years ago in KDD, right? And it does hierarchical adjustment using elementary operations, right? And so what they do is they have this original hierarchy, and then there are three operations that they can perform. So what they could do is they could promote one of the children nodes to the higher level. So in this case, they promote A.2 to R, or they could demote someone, right? So they could take B and they could put it under A, or they could also merge, right? So they in this case, BC merges to form its own new node, and then B and C are the children. So there are these three operations. And the way this method worked was it said, there's this optimal hierarchy is near the neighborhood of the predefined hierarchy, and you search for the constrained optimal hierarchy by applying a sequence of these elementary operations and reevaluating, right? So they'll make one operation, and then they will assess whether the operation helped them or not, and based on that, they will keep it or not keep it, and they will keep on doing this process. But so after every elementary operation, you're keeping on doing this. So as you can imagine, this is not going to be easy or scalable. I think split is like the demote, right? So when you say split, so split is even harder to like characterize, right? Because you have some examples within the node, and now you got to make a decision which of these examples split into what nodes. Right. That's a good idea. I saw something like that 2 years ago for hierarchical classification. So the idea was, so these are one versus rest models, right? So they were training one versus one models. And when they were training the one versus one models, they said that there were some examples that didn't belong to either of those two classes. And that formed the split. So that was one idea. But it's really hard to define that. You'll see even in this case, it's going to be a little bit challenging to do this in a reasonable manner, right? In a time-efficient manner, I would say. Okay. But that's a good idea. Like in the future, you might see those ideas come about. All right. So the goal is to do this so these are essentially, you started from edge 0, you made this decision to go to H3, you could go to H4, you could go to H5, H6, H7, or you could roll back and go to some other. So it's essentially like an optimization where you're making one change, you're evaluating whether the change made sense or not, and you're redoing this. So given these constraints, anything that was iterative wasn't a good solution for that constraints that we set up. 1,000 classes, lots of examples at least, and lots of features, right? So it didn't really, this elementary-wise operations didn't make sense. So what we wanted to go to was a wrapper-based approach, which means that, so the wrapper-based approach requires this evaluation of hierarchy at each step, which is computationally expensive. What we want to go is from the wrapper to a filter-based approach, right? So a filter-based approach is you take the data, you have your hierarchy, you do one step, you change your hierarchy, and you move on, right? So there's no reiteration going to happen. So essentially, that's one of the key ideas that we're going to change here. So the wrapper base involves, we'll generate the neighbor hierarchies for edge 0, we'll train different hierarchical classification models for each neighbor on the data set, we'll evaluate the hierarchical classification classifiers on a validation set, we'll pick the best neighbor hierarchy as edge 0, and until we see any improvement, we will repeat this continuously. We'll repeat this continuously. Okay. So this is the original Tang 2006 approach. So this was a data set that they used in their paper in 2006. This was there was two data sets, soccer data set and kids data set, I believe. Soccer has 83 nodes, kids has 299 nodes. The number of leaf nodes are 69 here, 244 here. The height of the tree is 4 and 5, and here the total number of training examples and features. Okay. So first, I just want to show the results, right? So these are the macro recall now, macro F measure. Number of features, so you can also choose some features, right? And based on the number of features you choose. We also show results for this, we get this question a lot, like, what if you just do clustering? Forget about the hierarchy, do clustering. So this is just to show that clustering is not going to be the best way to go about, best way to do this, right? So what you'll see is that here's the clustering results. In blue are the results using the original hierarchy, which means you assume that the hierarchy is correct and you run your classifier. And this is the adjusted hierarchy. So clearly the adjusted hierarchy is showing improvement on these two data sets with this method. So when you modify the hierarchy using these elementary wise operations, you're getting better results, which means there is merit in doing that. And the question is, can we do this faster? So one of the methods that we proposed was a filter-based rewiring strategy. So for large-scale data sets, any sort of iterations can become intractable due to these multiple hierarchy evaluations. We don't want to do this computation multiple times. So our objective was to modify the predefined hierarchy using a filter-based rewiring strategy that does not require multiple hierarchy evaluation without significant loss in performance. So we assume that even if we get some hit compared to the elementary, that the Tang et al. Approach, it's acceptable as long as we can do it for large number of classes. So our strategy is we have a similar step. We have an original hierarchy. We can create a new node. We can delete a node, and we can do a rewiring. So we can do these three steps, which are like the promote, demote, and merge, but we like to call them these three. They're a little bit different in the way they operate. So these two can happen at the first steps, and the node deletion can only happen at the second step. So there is a phase one, and in phase one we can only do node creation and rewiring, and in phase two we will delete anything that is useless, which is the node deletion. So we start by a predefined hierarchy. We compute using a small validation set pairwise similarity between the examples of the different documents. So now we're not using any classification based accuracy or anything. We're just saying, given the data that we have, can we compute pairwise similarities on a small set? Based on these pairwise similarity, we then go and using some rules, we identify correct inconsistencies, and we come up with this adjusted hierarchy. So we group together the fundamental idea is we group together the most similar classes, and we keep on identifying inconsistencies within the hierarchy. So we say that if classes that are supposed to be the most similar are in different branches of the tree, then that's a problem. Right? So can we resolve that by splitting them or by moving them around? And then we apply those the parent-child rewiring and node creation to these inconsistencies. And at the end, we perform post-processing, which is node deletion, whenever we have some inconsistencies at the end. Okay. So remember, I showed you this. This is something funny going on with the 16 by 9 display, but this was the news group study. So this, I showed you this earlier. This was the original hierarchy, and these were two modifications, right? And this modification was with the flattening approach, right? So with that global INR flattening approach. Okay. And this modification is with the parent-child rewiring or the rewiring type approach. And with the rewiring, what you first of all see is that, remember there was this consistency here about this society and religion. So that gets correctly put together. Politics gets modified a little bit to include these topics. And comp sci gets created as a new node, which doesn't exist here, to include graphics, Windows, and electronics. And there's still comp, which has OS, MS Windows, and miscellaneous, right? So these are news articles or news forum articles about these things. And in terms of, if you could see this, then the macro F1 for the leaf nodes, again, which are consistent everywhere, for this rewired hierarchy is going to be 3 to 4% better than just our original result. So I'll talk about it. So the complexity is to compute the pairwise similarity between all the nodes that exist within your hierarchy. So if you have
nodes or all nodes?
So it's all the nodes. It's all the nodes. And but you use a small set. So we also tried this. So it's pairwise. It's n. If n is the number of nodes, it's n squared, and then your similarity function, which is number of examples within each node, times those examples. But we use a locality-sensitive hashing type technique to do this quickly, compared to just a simple pairwise similarity. So TEZ was that method in 2006, which we modified to make it even applicable to some of the data sets that we are studying. is slightly better due to the brute force method to find the optimal hierarchy. But TEZ is very expensive and not scalable for large data sets, right? So here are the data sets that we are studying so far. Here is TDLR, which is top-down logistic regression, no changes to the hierarchy. Here is clustering, where you take the data, you cluster, you find the hierarchy, and you use that. Flattening, which we talked about earlier, and the two rewiring methods, the reW hire, which is a new method here, and the TEZ, right? So anything that is in triangle is statistically significant compared to the flat method. In this case, of course, the TEZ is doing much better on the smaller data sets, but it's an optimal way of doing that, which doesn't really scale to the larger problems. Okay. So we'll talk a little bit more about the time that it takes by seeing the number of operations and things like that. So here is a hierarchical measure. So I want to caution you with this because I personally don't like to use the hierarchical measure because the hierarchy has changed underlying, right? So the way we do this is, just to be fair, we said if we took the original hierarchy and evaluated, even though we changed it in our results, assume the original hierarchy and then evaluated the results, and also took the modified hierarchy and evaluated using the modified results. So we do both of these, right? So I wouldn't look too much into it, just it's more informative. Like when you do some changes, you should be fair about how to evaluate, and it's not clear to me how to best evaluate using these metrics. So TEZ method is very expensive. It's approximately 20 times more expensive on the IPC, on the patent data set. So these are essentially runtime in minutes for the training. So the rewire hire is about 1284 minutes versus about 26,000 minutes here. And for the large data sets, not scalable. But it's the highest compared to not doing anything, not fixing the hierarchy at all, a flattening method versus the rewire. So it's not super, it is expensive, but not prohibitive, I would say. So if you look a little bit under how many operations, elementary operations are executed. So for the smaller data sets, we can do this comparison. So for the IPC, which is the largest data sets, there were 412 recomputations of the hierarchy for that elementary wise operation, which is a lot. In our case, we have 42 operations, but they're done in one shot. So we are not doing 42 steps of retraining and testing. There's 42 operations done in one shot. So it's a little bit. So we get performance boost from both from doing it this way. So we also assess what is the effect of varying the percentage of training size. So this is essentially looking at the learning curves, right? So look at the learning curves to see what happens when you have lesser data versus a lot more data. So we go from smaller training size to all the way to larger training size, 100% training. And the TEZ we could evaluate on the small data set, but not on this one. So you can see that it lies in between, and then it improves after some time. So which means that if you have less data, then it might be easier to do this global one-shot method versus this elementary-wise operations. So our initial goal was only to use a hierarchy with the top-down methods, because so the scenario was you have the hierarchy, it has some inconsistencies. Let's modify that and use it with the top-down method, so we get the benefit of doing faster prediction. We don't want to use the flat method, but we also tried we took the so you have the expert defined, the original one, the TDLR top-down applied on the rewired one, but the higher cost, which we talked about earlier, on the original one, and the higher cost on the rewired one. So the higher cost on the rewired one, of course, gives us the best results. So if you now have the best hierarchy, and you apply the most sophisticated hierarchical classification method, then it gives you even more performance. So essentially, it's a step, and this is the percentage improvement over the flat model. So the flat model is like a baseline. We're showing the percentage improvement over the flat models for these three data sets here. We also wanted to show the comparison to flat TDLR and higher cost approach for essentially how many classes do we improve upon, right? So the question was, we are seeing 5% improvement on macro F1, 3% improvement in micro F1. And this essentially is more equipped to like reviewer, writing response to reviewers when you get your papers rejected, right? So it's like, So this is not very exciting, but it's really exciting because you're improving close to like 80% of classes where you're showing improvement with your approach, right? So 80% of classes are showing at least some percentage of improvement. So this was an important finding here. So again, we want to show that we have TDLR plus expert defined, TDLR plus rewired hierarchy, higher cost plus expert defined, and higher cost plus rewired hierarchy. So we show that it really has a good performance improvement. So our proposed, we have different approaches for flattening, level-wise, local, global, and then we have this data-driven rewiring approach, and it works really well for classes with rare categories. And it works well. So you asked that how much time does it take for computation, and it works well for large-scale data sets due to these embarrassingly parallel steps. Right, computing pairwise similarities, again, embarrassingly parallel. So very like attuned to that it's easy to do this computation if you have a large number of nodes. So let me take a step back and just give a recap. So now we had, we said now the hierarchy, we had all these nice hierarchical classification methods. They were not doing well, so we said, oh, the hierarchies might be inconsistent. So we came up with some ideas or presented some ideas on how to resolve those inconsistencies. And if you resolve those inconsistencies, then you can either use top-down if you care about prediction time. If you care about performance, you want to use HRLR or higher cost with the rewired hierarchy. Okay. Any questions, thoughts?
When you use a clustering method, how did you start from the bottom of it?
Yeah, so it's an agglomerative clustering. So we define different thresholds. I think they test, in these methods, they will test for different cuts of the tree and then see which one gives you the best result. You could also do some threshold, like percentage threshold, like you could say that if it's beyond this, then I don't want to go on. Yes. It is, but it's in a, it is available online too, but it's without any documentation. And students graduate before they finish things, right? But yeah, Azad has made it available. It's part of the papers that we have published. Any other questions? Yes. Let me think about that. So it usually has high true negative, high false positive, sorry, because those nodes are being, we did an analysis of that. So we said what happens at different levels. And I think at higher levels, you get misclassified into other nodes. And at lower levels, the reverse starts happening. But we have those exact, like, precision recall, percentage of the TPR rate and the FPR rate for those different levels. Yeah. So we do TF-IDF with standard Euclidean normalization or unit norm normalization. We just treated them as TF-IDFs, yeah. Didn't do any stemming or stopping. Means you could do that. Again, that wasn't the focus of our work. Well, the flattening approach is you mean the rewiring one, the 2006 one? So that's what the 2006 one is called. It's the Tang et al. We call it the TEZ in our papers. There wasn't anything. It doesn't really scale, so it's hard to expand that. So the approach that we have is slightly different than that. We didn't see any other ones. All right, so I want to move on to this, what I call the last phase, which is much more advanced topics, I would say. At least I consider them to be like more like cutting edge in this hierarchical classification space in terms of like new research, right? And there's some practical applications that we found in CERT as well. So by now you all should, you've been in this room for like 3 hours at least. So hierarchies are very common, right? You believe this. They're so common that for different applications, different people define their own versions of the hierarchy, right? Or different scientists will say, I trust this one, but I don't trust this one, right? Or there are multiple hierarchies that exist for the same data set or the same instantiation of that data set. And this is much more common in biology, right? So I'll give you some examples here. So our motivation was, can this heterogeneous or complementary view of these hierarchical data sources provide us additional knowledge which can be exploited by the classification framework? So can we learn from these multiple hierarchies?
All that cubes are going to have hierarchies on time and hierarchies on geography.
Right, right.
That you can multiple ways of subdividing dimensions of
Yeah, yeah, so in some way, but my example will be a little bit more slightly different from that. I think you're just focusing on one of the variables here, but mine is like if you look at all these variables, then different folks might focus on different angles. So common examples are this is a protein structure classification, which is essentially my graduate work, which was now some time ago. So I think I gave this example. The common case is if you don't remember high school biology, my view is a 1 minute tutorial, which is we have lots of cells. Each cell has DNA. Part of the DNA has genes. Genes they do all the business. Genes get converted to proteins, and proteins react with other proteins, and they do more business. They do all the fun business for us. And essentially, so the proteins, right? When you say I sequenced a genome, right? After that, there are lots of steps, right? Just sequencing a genome by itself is useless, right? After that, there's all this like ton of things that we need to do. We need to figure out where the genes are. We need to figure out what the genes do. We need to figure out which proteins they produce under what conditions, and which proteins react with which other proteins, and what do they do at that level. Okay. So sequence by itself just gives you information about a protein sequence. It tells you what the protein sequence looks like. But ideally, protein is not a sequence, right? It's a structure. It's a 3D structure, and it's that 3D structure that lots of biologists and structural biologists in particular are passionate about, right? They want to figure out the 3D structure of these proteins, right? And when they do a X-ray experiment or an NMR crystallography experiment, they will say, here is what the 3D coordinates of the different atoms of the protein look like. They will visualize that, and based on that, there are some automated and semi-automated methods too. But based on that, they'll put it in a hierarchy. So here is a protein hierarchy. It's called a SCOP or CAT, and they'll say, here is the hierarchical definition of this protein. Now, this is all done based on structure, 3D structure. Unfortunately, 3D structure is expensive, and it's time laborious, and it's not as high throughput as all these genomic technologies, right? Which find all these genes and find all the protein sequences. So our goal as bioinformaticians is to, given a sequence of a protein, can I classify that, or can I first predict the 3D structure if I can, right? So given a sequence, which is nothing more than a sequence of characters, sequence of 20 amino acid residues, can I figure out where each of these atoms lie in 3D space? And if I can do that, I'm doing protein structure prediction problem. And related to that is, given a sequence, can I classify this protein sequence into one of those hierarchical definitions of these protein structures, right? So that's essentially the protein structure classification. Now, when I was struggling with that, even at that time, there were these US biologists, structural biologists, and these UK biologists, and they would not agree on what the structural classification definition should be. Right? So there was one database called the SCOP, which was based in the United States, and still is, and there's another called CAT. And they're all trying to do the same thing. They're taking a 3D structure and putting it into these hierarchies, but they have different definitions, right? So the hierarchy views for the same protein structure is different. Now, if you want to understand what a protein function does, that's even more complex. So there's a database called the Gene Ontology database, which I think KDD, you'll see some papers that say, we're doing protein function prediction using this database. But that's just one of the 27 different databases that exist for protein function. Right? And these are all hierarchical in nature. So there's this hierarchy thread that's going through. So when I looked at this, I said, given a protein instance that I want to classify into its structural definition, can I use two databases? Can I use the SCOP and the CAT together to exploit any complementary relationships that exist to classify them in both these databases together? Okay. And if I extend this, can I use this not only in SCOP and CAT, can I do this in multiple databases, like the protein function databases? And then we also said, several hierarchies exist for categorizing text documents or web documents, such as DMOZ and Wikipedia datasets. Can we exploit those together? Can we use them together to help one or both of them? Okay.
This basically becomes the hierarchical graph, where you may have common stuff.
Yeah, in a way, you can assume that there's a super root node and the super root node. But essentially, remember this, there are multiple views of the same instance now, right? So each example could belong to both the databases, but they have different paths, right? And different relationships which you want to exploit together. Okay? So our objective is to utilize these multiple hierarchical label views within the multitask learning context to improve the classification performance. So instead of me talking so much, right, a diagram will help, right? So if you think about how you want to do this, let's assume that there is this red hierarchy and there is this blue hierarchy. They both are different sources, right? They both have different instances. And my goal is, given a new example, tell me that it belongs to A.2 A and R, and it belongs to, in this, it belongs to A.2 A and R. So, or maybe it belongs here in B.1 B and R. I don't know, and because this is a different hierarchy. So one approach is don't do anything about it, which is ignore everything, right? So that's why I don't have any edges here. I don't have any relationships here. And I don't have any complementary relationships that I want to exploit here. The other view is what we already learned, which is single hierarchy, which is, relationship between the tasks within a hierarchy should be combined, but across the tasks, don't do anything about it. And then multiple hierarchy multitask learning, which is you somehow figure out what the relationships between the different nodes are and exploit them so that you will get better results later on. Okay? So the goal will be now, somehow I'll be able to say that B is mapped to A and B.1 is mapped to A.2 and B.2 is mapped to A.1, or B, for example, B.1 is mapped to A.1 30% and is mapped to A.2 60%, and I would like to leverage this in my optimization when I do the multitask learning type formulations. So nothing's changed, right? Nothing's changed except the only complexity that I've added so far is I've added the relationships across these multiple hierarchies. Okay, that's the only thing I'm changing, right? So if you go back to 230, right? We talked about that HRLR, right? Which said parent and child are similar. Now I'm not only going to say that, I'm also going to say parent and child are similar, but there are some cross relationships, right? So these nodes also should be similar. So can we exploit that, and can we leverage that to build some better models? So we go back to our MTL formulation. So this is again a refresher on that, right? So again, the optimization happens across all the nodes in the two databases. All the examples, which is I is equal to 1 over NT. There's some loss function here, and there is some regularizer, and the regularizer does interesting things to capture these relationships, right? The simplest one, the one that does a little bit more than not combining them at all, is what it says sparse. It says all tasks will share a single set of useful features. They'll say all tasks, right? Doesn't matter whether you come from this database or this database. All these nodes will have some common features. Now, this is a very naive assumption if you think about that, right? So all tasks should have the same common set of features is not a good assumption actually, but it's a good naive first test assumption to see how the baselines stack up. But then these two are much more interesting, and this one is easier to explain because we already did this. All it says is that related tasks have similar parameters. So parent and child will have the same parameters, and nodes which are similar based on any mapping, expert defined mapping or mapping that you can compute, will be similar to each other. Okay? Now this one is a little bit harder to explain, but all it says is that the task parameters are drawn from some low dimensional common subspace, right? So it's like this, but a little bit better, because now I assume there's some common subspaces that exist between the tasks, and you need to find this trace norm of that large W matrix to compute that. Okay? So we tried, different loss functions. We tried these different regularizers, but to solve this problem, where given a new example, I would like to classify it into this red tree and this blue tree jointly. Okay? So let's go to our data sets. I didn't spend too much time. I didn't want to go into the application here, but SCOP and CAT are two of these protein structure databases that are very popular. right? If you were doing protein structure classification, you would be using these two data sets. And what I'm showing you is essentially the percentage improvement, or you can see from these plots the improvements that you get when you use these different techniques. Now, there's some interesting caveats here. There are 3 curves that are bunched up here, right? So the 3 curves include the single task learning, which doesn't do anything, and the single hierarchy multitask learning, right? One is the graph, one is the trace. One uses the parent-child, one uses the trace. Now, I didn't show the sparse one because it was useless. It didn't do very well. The graph multi-hierarchical multitask learning and the trace multi-hierarchy multitask learning are out here, and they have like a 5% improvement, which is a big improvement in this space, right? 5% is a really big improvement. And in this case, this is the cat, and for cat, it doesn't show any improvement. So it was interesting that we combined them, and for one of the sources, it helps it, but for the other one, it didn't show any improvement. So for some reason, this is all empirical. I don't know why, and I'm still trying to figure out. For some of the benchmarks, it did very well, right? When we combine them. For the other side, it didn't do well. So for SCOP, it does very well, but for cat, it doesn't do very well. So SCOP is like a parasite. It benefits from cat, but cat doesn't get anything in return here. Okay. So we just I show you a scatter plot between the single task learning and the SHMTL. You see there's not much improvement, but when you use MHMTL or multiple hierarchy multitask learning in comparison to single hierarchy multitask learning, you see there are more blue triangles on the winning sides for both the graph and the trace regularization, and that just shows there's much more benefit to the SCOP versus the cat for some reason. And it's not that the cat is doing awfully bad. It's not getting a boost. It's not getting the boost that the SCOP is getting. So we did this setting for protein data sets, and then another student of mine did this on text data sets. So he did it for Wikipedia, and he showed that Wikipedia, if you wanted to classify documents in Wikipedia, it does help if you want to use DMOZ data set. The DMOZ, which is another text data set. So it helps to combine them. And then I think in 2014, after 2014, the large scale hierarchical text classification challenge, if you look at that, it has now multiple tasks. So it has a task on this multitask learning type approaches. So they also have, I think, aligned to this view that there are different database sources for the same data per se. And if you combine them, you might get some benefits. And this is what the benefits are. So I just wanted to share with you this topic that I think is really, I think it's interesting that it can be extended beyond that. Yeah, so this we didn't do that yet, but that's a good point. So I think for the text data set we do that, but I'm not presenting those results yet. That's a great point. I want to do it for the bio data set because it's much more relevant. The biologists will be really happy after that. Yeah, I don't have a good answer for that right now, but that's a great point. And something that is really caught on in the past 3-4 years is this problem of extreme classification, and also sometimes gets confused as deep learning, right? So deep learning is very popular. Deep learning has its own separate track, separate definition now. But initially, when these models came about, they used to call them deep classification, right? So I want to not call them deep classification. I just want to call them extreme classification, right? And extreme classification is many real-world problems with multi-class and multi-labels, which involve an extremely large number of labels or output space. So extremely large means not now 100,000, but millions, right? So you want to go into the million space now, and you want to solve those kind of problems. So the goal is to learning classifiers corresponding to each label is almost an impossible task, right? If you have to learn million models, it's going to be really hard. It's going to be challenging. There is interlabel dependency may not be available. And typical examples are you want to predict hashtags from tweets. As tweets are coming, right, you want to recommend to to people different tweets. So one idea is that you could classify the tweets to the hashtags, and you could reclassify your old tweets to go back to the currently evolved hashtags. The other one is the LSHTC ran a competition where you want to predict Wikipedia tags from documents. So tags can be anything, right? I can go define a tag, and if that tag becomes popular, given a Wikipedia document, can I classify what tag it is? Okay. So the objective is, given these huge set of labels, identify the labels that can be assigned to unlabeled instances examples efficiently and accurately. And when efficiently means that we want to do this very, very quickly, and accurately has to be as accurate as possible. I know, I think you really like them, but in my opinion, association rule bindings don't give you anything useful, right? So you have a threshold, and if you set the threshold too stringent, then you wouldn't get anything, and if you set the threshold to this, then you'll get lots and lots of examples. So I think we can talk about that, but I don't know if that's the right context here. So statistical challenges is that as you increase in the number of classes, this is prone to decrease in accuracy due to complexity in discriminating between different classes, right? So as you get more and more classes, the discrimination power becomes less and less. And there are computational challenges, which is you want to train classifiers for a large number of classes, make it computationally infeasible, and you want to predict labels for unlabeled test instances, also compute-intensive tasks. There's also this notion when we talk about tweets, hashtag hasn't evolved, hasn't formed yet. So how do you know this is the right set of hashtags, or how do we move to beyond that? So there's some notion of orphan node prediction. So this was an example. This Minerio, I think he's at Microsoft Research. I think he came up with this idea of eigenpartition trees, which was a good idea. He computes some set of plausible labels, and so the basic premise will be that there'll be a two-phase approach. We'll compute some set of labels that we believe can be computed approximately. We don't know the exact answer, but that'll help us refine a model. So we'll take those small set and we'll go to the next step. So essentially, at each node, we try to send class examples exclusively to right or left. So there's some sort of a partitioning process going on altogether, and we want to ideally send the same number of examples left or right in the aggregate. And he does this optimization function, right? Or they do this optimization function. But the key idea is that expensive classifiers, if you had any, you would only try them on the scarce number of labels or plausible number of labels that exist. Okay? So they do this for this data sets like Twitter, LSHTC, and there's the average labels per examples, the total number of examples. These are million, the features, and the total number of classes, right? So I don't believe this is considered extreme, I think, but they try that, and you can see the number of classes is 200,000, and this was 3 years ago now. So these benchmarks have increased tremendously. And if you're interested in these topics, then there are some workshops that are called extreme learning examples, extreme learning, not to be confused by extreme learning machines, which is completely different again. Right? So this is some results on that LSHTC data set. This was published in SIG-KDD, where there's a node partition formulation which optimizes a ranking function over the labels, and then there is this method X1, where the effective number of labels is reduced by projecting them into some from high to the low dimensional space. So these are precision at 1, 3, and 5. So the way these are evaluated is you give the top 1 candidate and you say whether you get the top 1 candidate correct or not. You give the top 3 candidates and you see if you get this. So it's a more ranking type of retrieval or ranking type evaluation. And inference speed is a metric that came about here, which is how many examples can you process per second, right? So here you can process 2,000 examples per second, 1,000 examples per second. Now again, I'm not listing the hardware, but I'm assuming that they are consistent here. They all are done on the same hardware. So this was this work by called deep classification by Xu et al. At SIG-IR, and essentially the key idea is similar, that these large-scale taxonomies are prevalent due to more specific topic class-related information, and the traditional algorithms for hierarchical classification may not apply, so they will follow a very simple approach, which is, so I'll tell you how the approach works. You have a training set, you have some very fast index, you have your new document. You compute pairwise similarity using the index very quickly, like a hashing type technique. You'll get candidate categories. So you'll say, I have some threshold. I found 20 similar documents. These 20 similar documents belong to 3 classes, right? And for these 3 classes, I'll train a classifier to distinguish between 3 classes. But I'll train the classifier real time. So I will not pre-train it. I'll just train it on the fly. So then they'll train a classifier, and then there'll be a classification, and there'll be a category. So this method has been winning some of these benchmarks, like these larger competition. Very simplistic, but works very well in practice. So it's a nice algorithm that works very well. This is a large hierarchy, can be pruned into a smaller subset of hierarchy with candidate categories. So again, if these were my candidate categories, then essentially I use them to build the tree, and then I use only this small tree to do any hierarchical classification later. Okay, so that was one of the other approaches. So I'm not spending too much time here, but there's a data set, if you're interested here, open directory project data set that can be used for this evaluation. And it shows you the number of examples again at the different levels. And the deep classification is one of the methods that does very well at all the different levels compared to the hierarchical SVM and the search-based strategy. Some of these other HRLR and some of these methods are not even applicable just because you cannot fire so many leaf nodes. So a deep classification with a higher cost or with a HRLR may make sense. Instead of doing a flat method, you could do a hierarchically inspired SVM. So I'm going to skip this one in the interest of time, but what I want to conclude by is saying that this is an interesting problem. I believe that it cross-applies in different domains, so that's what makes it exciting. Today we talked a lot about various challenges with them, discussed some approaches to do hierarchical classification, maybe not extreme, but at least large, right? And some of the emerging topics, which one of them we talked about is this large scale classification with these deep hierarchies, right? With this large number of examples, large levels, large number of levels, things like that. And then another thing we didn't really talk about is orphan node prediction, which I kind of hinted at, which is, your data evolves so that your class definitions are no longer prevalent. So there's a new class that has emerged, and how do you detect that? And how do you account for that? What do you do for that? So there are some ideas around that. Azad spent some time doing that. He wasn't very fruitful, so don't have much clue on what to do in that space. But there is some work by, as I said, Will Cohen on that, and that's pretty interesting. Some references here. So all these slides are online. If you follow KDD 17, go to their tutorial page and you link through. That's one way. The other way is it's right out here. There's a missing tilde out here, and that's the reference. But I'll take any final questions if you have any. This usually means this usually means 2 things, right? Either everything went well or everything went away. All right, so thank you for coming, and I'll see you in the conference.